Alright guys, in today's lesson, we will be looking at higher order derivatives. In other words, you can actually take more than just the first derivative or one derivative. So a few things we're going to try to accomplish today. One of them is to recognize the notation for higher derivatives. And then I will show you how to find higher derivative given a function. And also we're gonna also try to recognize and review that derivative as slopes of the tangent lines. So first, let's start out with the notation of the first derivative, and we have been working on this for the last few days now. F prime is used to represent the first derivative, or we also use the derivative of the function. This is another symbol for the first derivative. We also use y prime of x as notation for the first derivative. So what is the notation for the second derivative? Well, it is actually very simple. But in order for a second derivative to exist, we need to know that and confirm that the function and the first derivative are differentiable. Then the second derivative will exist. Now, what is the notation for the second derivative? Well, it is f double prime, okay, or y double prime, okay, or sometimes you will see d square y over dx squared. Those are notations for the second derivative. So this might confuse you. So maybe let me help you to discover this notation. When we say, for example, f double prime, we're really saying the derivative of the first derivative. That's f double prime. See? Or when we say like y double prime, we're really saying the derivative of the first derivative, and this is the notation for the first derivative. All right, so when you multiply the variable or the letters together, don't you get 2 d's followed by a y, and 2 d's is d squared. When you multiply these together, don't you get like 2 dx's? We call that dx squared. Okay, so these are just notations. So when you see that, you know that you're asked for the second derivative. When you see either one of these, you ask for the second derivative. Okay, awesome. So here's your first example. Find the second derivative of this function. Start by using the power rule to find the first derivative. Bring down the exponent. Subtract the original power by 1. Bring down the exponent. And then the last number, which is 2, the derivative is equal to 0. What you have just found is the first derivative, and now we proceed to find the derivative again to attain the second derivative. So the second derivative is, once again, apply the power rule to the first derivative. So what do we get? We get 6x minus 6, and we're done. So this is the second derivative function, and later on in toward the end of unit 2, and especially at the beginning of unit 3, we're going to be using the second derivative a lot, and I'll tell you more what the meaning of the second derivative is. Now, in addition to the second derivative, you can go ahead and take a third derivative if you want, a fourth derivative if we need to. So higher order derivatives do exist, and they are labeled as f double prime for second derivative, f triple prime for the third derivative. Anything that's higher than Then 3, we just go, well, if we're looking at a fourth derivative, then we're just going to use the number 4. If we're looking at a fifth derivative, then we're going to use just the number 5. So anything above a 3, you're just going to explicitly use the number. Awesome. All right, here it is. Find the third derivative of this function. So we begin by finding the first derivative. 2x minus 3, and then we find the second derivative. That would give us 2, okay? And then find the third, and that would give us 0. All right, so the third derivative is equal to 0. There we go. Awesome. Find the fourth order. We can refer to as the fourth order, but we're looking at we're looking to find the fourth derivative of this function. So let's try the first. All right, so you have a few options here. We can use the quotient rule, or we can use the power rule. I would opt for the power rule, so I need to rewrite my function as a power. So this is x raised to the negative 1. All right, so the first f prime is going to be bring down the negative, so you have negative x, and then you subtract the original power by 1. Find f double prime, bring down the power again, that becomes a 2, because you have a negative 2 times negative 1, that's negative 2. Subtract the original power by 1. That's the second derivative, and you're finding the third derivative. Bring that down, that becomes a minus 6. Subtract the original power by 1. And then here's your fourth. Bring that down, that becomes 24. Subtract the original power by 1. Okay, so you can leave your answer like that, or the preferred way of expressing that answer is 24 over x to the 5th. Awesome. Great job. Now we know that derivatives are slopes of the tangent line. We have been discussing about derivatives as slopes. So is it possible to look at a function and then use the derivative function to find where the slope equals to 0? And where the slope equals to 0 is referred to as horizontal. Where the tangent line is horizontal to the graph means that where the slope equals to 0. So let's go ahead and sketch this graph of the function x squared minus 4x. If you sketch the graph correctly, then the graph will look something like this. Okay, this is your x-axis, this is your y-axis, 0, 4, and then at the point 2. And if you look clearly, at 2 is where the slope of the tangent line is horizontal to the x-axis. To answer this question with a graph, we can say that the x value where the tangent line is horizontal is at x equals to 2. But for more complicated functions, we won't be able to use this method. So we have to learn how to do it analytically, which is by algebraic method. So we're trying to find the x value where the slope of the tangent line is horizontal. So we start by finding the derivative function, because the derivative function tells us the slope at any points. And if we want the slope, we want to know where the slope is equal to 0. horizontal line means that the slope is 0. We replace this symbol with the number 0, and then we solve for x, and if you do it correctly, you can kind of see that x equals to 2. So x equals to 2, that's where the tangent line is horizontal to the graph. Beautiful. All right, let's try example number 5. Find all the points on the graph of this function at which the slope of the tangent line is equal to 1. So let's do it without looking at the graph, and then we'll confirm the graph with the graphing calculator. So I want the tangent line with the slope of 1. I start by finding the derivative because it is the slope function. 3x squared, right, minus 2. I want the slope to be 1, so I replace this number or this symbol with the number 1. And then I proceed to solve for x by adding 2 to both sides. That leaves us with 3 equals to 3x squared. Divide both sides by 3, leaves us with 1 equals to x squared. Now, there are two possibilities. X can be -1 or x can be 1, because both of them, when squared, gives you 1. So, there are 2 points on the graph. There are 2 points on the graph that produces a slope of 1. Those 2 points are x equals to -1 and x equals to 1. We can also use a calculator to confirm our findings. So x cubed minus 2x, and then we're just gonna graph standard zoom 6 is standard window, and I want you to pay attention to -1 and 1. Okay, I'm gonna zoom in, I'm gonna fix the window screen here so that you get a better view of what we want to see. I want you to see that at -1 and 1, they have the same slope. So at -1, you see how the slope goes like this, and at 1, the slope also goes like this. So they have the same slope. They have the same slope. Awesome. The last thing on our agenda today is for us to find the equation of the tangent line, which is what we have been doing for the last few days, but it is on the quiz. It has been a struggle for some of you, so it is important that I laid out the foundation for you to succeed when creating the equation of a tangent line. So, 3 things that you need when you are asked to write the equation of a tangent line. You need to know the slope of that line. You need to know a point on the line. And you need to know the form to use. Let's start with, let's do a couple of examples here. Find the equation of the tangent line to this function at x equals to 5. So what I did was I kind of removed all the unnecessary graph, and I just kind of zoom in between 1 to 7 so that you can see what the graph looks like. Okay, and I want to know what is the equation of this tangent line at x equals to 5. In order to do that, in order to write an equation to model this line, which is this equation, I need to know the slope of this line. So let me use my highlighter here. What is the slope of that line? So I start. If I know the function of the graph, then I can find the slope at any point. So I have to start by finding the derivative because it gives me the slope. Now, I want to know the slope at 5. So I plug 5 in for x, and voila, we get 10. So we know that the slope is 10. We need to also find a point on the line. The cool thing is you know the x values, which is 5. And a point on the line also happens to be a point on the graph. So you can just take x equals to 5 and plug it in here to the function to find the y values, or the y value. So when we plug 5 in there, we get 25. So y is equal to 25. We have a slope, we have a point, and the next thing we do is we generate the equation. So equation is y minus y1 equals to m times x minus x1. Now your y1 are these values, your y1 and x1 are these values. So you take those and you plug them into the appropriate order. Your m is your slope, so replace that with the number 10. And then your x1 is the number 5. And then now is where you distribute. And then you add 25 to both sides. And that leaves you with 10x minus 25, which is what we got over here. So you can express your answer in this form or in this form, but you need to know how to do both. Alright guys, last problem. Suppose that f1 equals to 4. By reading this statement, that's my point. So I know that when x equals to 1, y equals to 4. That's what f1 equals to 4 means. That's the x value, that's the y value. This is your slope function. The dy over dx, that's the derivative, which is your slope function. So I know that the slope function is this. Find the equation of the tangent line to the original function, which I don't care what it looks like, and I don't need to know what it looks like, but with this I can find the slope, which is what I need. So we want to find what is the slope when x equals to 1. So now what you do is you replace x by 1 into this function, 1 minus 1 squared. Clearly you have a slope of 0. Alright, so you have the point. Now you can start forming your equation. So y minus 4, slope is 0, and then x minus 1. The cool thing is 0 times anything is 0, so here's what we're left with. And that means that we have y equals to 4. That is the equation of a line. So guess what? This is a horizontal tangent line to the original graph. Awesome job, guys. I will see you guys later.